Hello, America. After a 3-year hibernation, it's time for us to return to the surface and get about the job of restoring our planet. For those of you who haven't been there yet, it is a very different place. A place of perpetual twilight. The air still hasn't cleared completely, and the sun struggles to get through the haze most days. And as a result, everything has changed. You will see large expanses of burnt-out forest, not a whole lot of living plant life, but endless expanses of something else. Fungus. That's right, mushrooms. The only kind of life that really thrives in this sort of environment. Fortunately, the winter did not last as long as we anticipated. The huge amount of carbon dioxide that was released into the atmosphere began to compensate for the amount of sunlight that we were losing, and the world's temperature is beginning to warm up rapidly. And this environment of very little sunlight and a great deal of decaying plant life has provided an ideal environment for this new dominant life form on our planet to survive. It is truly amazing. And it has happened before, but it isn't going to be a permanent thing. Must emphasize that. Most forms of plant life, they leave behind seedlings in the aftermath of a massive fire, encapsulated life that will begin to recover. However, animal life, the oceans, all of that was significantly disrupted. Most forms of life in the shallow seas are gone, or their stocks seriously depleted, and we can't expect that to fully recover for generations. And that's something we need to remember. We are working not for ourselves, not to restore the earth to what it was in our lifetimes, but for future lifetimes. But if you're still alive now, and you can hear the sound of my voice, that means you have an instinct for survival. You have the strength to push on and to carry out your responsibilities of restoring this planet, no matter how long it takes. And that's something... Is this thing on? All right, we don't have a great deal of time. Some of you may have heard rumors of an organization that seized control of one of our underground facilities. Since that time, they have gained access to a massive National Guard armory and somehow learned of the locations of the rest of our underground havens. And they have begun a coordinated effort to seize control of all of them. Even here, in this place, we are compromised. Amazing. In the meantime, you must emerge from your shelters as rapidly as possible. We are providing the locations of the other active facilities to you so that you can coordinate defense. Tragically, in this time when we should be focusing on survival and rebuilding, we must prepare to fight again.
On your feet, Mr. President.
I'll surrender this facility if it will save lives.
It won't even save yours.
So a lot of you may be pleased to hear that that's it for President Angry, and if you want to see more dramatizations like that, just let me know. I spent a few years as a stage actor, so I kind of enjoy that sort of thing, but at the same time, we also need to have a conversation about what is really likely to happen. Obviously, something like a massive planet-killer asteroid and an extinction-level event is extremely unlikely in our lifetimes, but nevertheless, that doesn't mean that there isn't going to be some sort of incident that's going to impact the lives of somebody on this planet within our lifetimes. And as a matter of fact, there have been two major incidents that have happened in Russia since the 1940s that have affected people on the ground. So what's likely to happen? Let's return to our tour of the Spaceguard Centre. Mr. Tsay, what are we looking at right now?
Well, that's the latest data from the United States on airburst events, large fireballs that are really quite noticeable most of the time. Some are going to detonate, relatively high in the atmosphere, not really a problem. Some of them, of course, the bigger ones or the stronger ones, will make it closer to the ground. And if they detonate quite close to the ground, then we're looking at quite significant damage. Everybody's heard of the Tunguska event back in 1908. That was an airburst. We're looking at an object probably somewhere between 40 and 60 meters across. And it detonated, well, it was 8 kilometers, 5 miles above the ground when it let go. But the explosion was about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The effects of that was simply to destroy the forest underneath. Just over 800 square miles, in fact. Which is about the same size as the Snowdonia National Park. That sort of thing's not terribly common. Smaller ones, everybody's heard of Chelyabinsk. That was actually very small, only about 17 meters across, and it popped 22 kilometers above the ground. The explosion was estimated at about 20 times the Hiroshima bomb. We were lucky there because it was some distance from the town of Chelyabinsk, so there was very little structural damage. Had it come in slightly steeper or detonated slightly closer to the city, then there would have been significant structural damage and probably loss of life. That sort of thing's really not that uncommon. Pretty rare for it to happen near a city or a populated area, but still quite a significant hazard. And of course, there's no geological evidence left behind. No crater, no thing that can be picked up in the years to come. So right now, we're not absolutely sure what the flux of these things are. And indeed, is it constant over time? There's a very strong body of opinion at the moment that the breakup of a large comet in the inner solar system could produce a period of vastly increased flux of this sort of thing, the airburst. Literally detonating atomic bomb-sized explosions globally for perhaps a few tens, maybe hundreds of years.
It's a frightening prospect indeed.
Well, it's one that we can't say hasn't happened because there's no geological evidence left behind. If you go back through history, and people are doing this right now, is trying to identify times in history where things have gone badly wrong on a regional or global basis. And then trying to identify any evidence we might find that this was caused by a sudden increase of the flux of small objects. It wouldn't surprise me personally at all if this sort of thing isn't relatively common.
Now, these things are obviously too small to be tracked. So that being the case, or at least not with our current systems, is there a way to where we may be able to track and prepare for things this small that can still cause a substantial amount of damage?
That all depends on the cost-benefit analysis. To find these things reliably would be really very expensive, certainly with current technology. And is the balance of the expenditure on the detection system compatible with the amount of damage that these things might do over a period of time? And this is what the politicians will look at before they allocate funding for programs like this. And the view, certainly we found when we briefed politicians, is that, the question is this going to happen before the next election? We've had that on more than one occasion. And if you say, well, luckily no, then they'll say, fine, not my problem then. No funding.
Now, if they were to ask the question, is this going to happen in my lifetime or my children's lifetime, how does that change your answer?
It changes it a little bit, but right now, frankly, we're so uncertain on the flux of these small objects, you can't really nail down, a credible number. We have the thought that there is a theoretical background to this. What we don't have are numbers to pin to it. And personally, in my view, this is a much more critical hazard than, the really big one every few millions of years. I'm personally fairly sanguine in that I think we can very nearly deal with the problem of, kilometre-sized objects and above. I'm not convinced that we've even given enough thought to huge numbers of small objects all hitting over a period of perhaps a century or so.
So what are we looking at here? You've shown me one telescope, which was a refractor, not so useful for tracking or anything. So what do we have here?
This is a 24-inch Schmidt camera. Now, it's not technically a telescope because there's nowhere to look through it, purely photographic. It was originally built by the famous Grub Parsons back in the late 1940s, when, dare one say, things were built properly. Was originally at the Institute of Astronomy in Cambridge, but because of various things, light pollution, the requirement to redevelop the site and so on, they decided to decommission this, mainly actually because nobody in the normal astronomical community is terribly interested in a wide field survey telescope. In the old days, professional astronomers would spend most of their time mapping the sky at ever-increasing accuracy. It wasn't until the Second World War when nuclear physics began to emerge that we really began to understand the principles of how stars work and so on and so on. Then the requirement was for telescopes that could produce very high resolution images of very small patches of sky. So most of the Schmidt cameras were either decommissioned or trashed. This one wasn't. And we were offered it because the guys at the Institute knew what we were doing and thought that rather than trying to palm it off on somebody else, they would offer it to us. Well, that was great, but of course we had nowhere to put it. We had no funding or anything like that, but it seemed to be too much of an opportunity just to say no. So we thought we'd give it a try, and since then, my volunteers, who are just awesome, have cleared the site, built the dome. All of this has been built by the volunteers. We've put the telescope or the camera in place, and we're now starting to work on the mechanics of the camera itself. The one thing we can't do is re-silver the primary mirror, so that at the moment is in an acid bath at the optical engineers in Essex to strip off all the old coatings. Then it'll be recoated and we'll have it back up here by the end of the year.
So to clarify, if you get this in operation, then this facility will transition to just tracking to tracking and detection?
Yeah, absolutely. Yeah. And the other thing that's quite important to note is that we're not funded by anybody, so we can look for stuff in bits of sky that nobody else looks at.
So once again, to re-emphasize, and I've mentioned this already in the video, you folks are called upon by the government to get information about this very important issue. However, the government does not fund you.
The government doesn't fund us. The UK government doesn't regard near-Earth objects as a hazard. Doesn't even appear on the Cabinet Office National Register of Risk. So all the data that we produce goes straight to the Minor Planet Centre in the States or to the European Space Agency. The UK has no part to play in this game at all.
Would it be helpful at all for viewers, my British viewers, and there are thousands of them, to call their MP to emphasize the importance of this sort of thing?
We often invite visitors up here to just drop a line to their local MP to find out what his view is on the subject of the near-Earth object hazard, if for no other reason to encourage him or his staff to do a little bit of research and find out what we're talking about.
Well, wonderful. And in the meantime, we're going to have a link in the description as to how to donate to this very important project.
Right? If it did hit at about a mile across, 1.5 kilometers-ish, that's going to be a really, really bad day. Not an extinction event. We're way below that. The main casualty here, having said that, we could expect about 30% of the human population to perish. The main casualty is the infrastructure, the technology that supports a modern civilization. That'll fail. So the survivors are literally just going to slip back into the Middle Ages.
Can you explain the method by which such a massive blast would wipe out our technology? Is it an electromagnetic pulse or something?
There's no electromagnetic pulse involved here. Well, minimal perhaps. The real problem is that nobody goes to work in a survival situation. If your world is falling apart, you've got global firestorms, you've got acid rain, possibly the same strength as battery acid. You've got the dusting of the upper atmosphere, so the sun doesn't shine. Are you really, really going to hop on your bike and punch in at work? Of course not. The first thing that fails in any major natural disaster is the local infrastructure. And with an object 1.5 kilometers in diameter, that local is global. So while your infrastructure will exist, it won't be working, which is a good thing, because down the line, when recovery starts, you've still got all the resources you need for that recovery, physical and intellectual. The infrastructure will take a lot of damage, I mean, mainly from the ejector, from the impact coming back down globally. You're looking at global firestorms. It's not going to be in good shape.
So 1.5 kilometers will create the sort of phenomena that people talk about with ejecta, superheated ejecta re-entering the atmosphere, heating up the atmosphere, and therefore absolutely causing, all the forests to catch fire, that sort of thing. So these consequences that occurred with the dinosaurs to a lesser degree, but still will happen with something this big.
Still significant, yeah, absolutely. And essentially, if you're underground, you're going to get away with it. If you're above ground, you might get away with it. This is not, as I said, a mass extinction event by any manner of means. But it's not going to be a nice time to be around.
Yeah, sounds quite awful indeed.
Yeah, but remember, as I said, the chances of this particular object hitting they're not zero. Now, we'll get that one straight. It's not zero, but it's vanishingly small.
But then you've also said that in this particular area, because of the brilliance of the sun, there could be others lurking out there, and we don't know much about the population of these
Absolutely.
objects.
Yeah. I mean, we're not 100% sure of the population of the main asteroid belt. There's loads of uncertainties here, mainly because while the search programs have ramped up significantly in the last 10 or 15 years, it's still not complete. So there's loads of stuff out there that we haven't found yet.
So the DART mission was a good first step. But at the same time, what I've been hearing you tell me during the duration of my visit here is that it's not nearly enough. There are many things we need to do in terms of other types of deflection methods, and also, it sounds like pressingly, a method to detect these inner solar system objects.
As we mentioned, if you haven't practiced it, you can't do it. So we can talk about gravity tractors, ablation, all of that sort of thing. But until we've done it, this is essentially science fiction. Until DART actually hit Dimorphos, that was science fiction. Well, now it's science fact. Good news. But with the other methods, which are almost certainly going to be needed for different types of asteroid or comet, we haven't really talked about comets,
right?
Then we've got to practice it.
Let me go ahead and ask that last question then about comets. Comets, of course, are a huge unknown factor because they come from the outer solar system. We certainly aren't aware of their population. I mean, do comets, how likely is that though, given, the infrequency of how often they pass through the inner solar system? The
real threat from comets that sort of keeps me awake at night, well, it's twofold. Firstly, of course, there's the large, long-period comet from the Oort cloud, which can appear from any direction because the Oort cloud is essentially spherical round the solar system. The short-period comets, they come from pretty much the plane of the solar system, from the Kuiper belt. But a long-period comet, a large one, with a high probability of impact, probably absolutely nothing we can do about it, because we'll only get a couple of years' notice. And if it's big enough, well, it's going to be a bad day.
So there's nothing, so incoming comets, even if we had a year's notice or something, probably no way to deflect it, not with current technology anyway.
But it is a vanishingly small risk, but it is the ultimate risk.
It sounds like it. Once again, Mr. Tate, you've given us a lot to think about today. I really appreciate it, and I wish you all the best with what you're trying to accomplish, and I'll get you all the help I can.
Thanks for coming.
Thank you. So here's the bottom line. Everything I've been talking about in this series of videos is not a reflection of what could happen if we don't take further action, but what will definitely happen someday unless we take decisive action. And we have the advantage of having the intelligence and the technology to actually be able to avoid these sorts of planet killer scenarios and extinction level events, but also to avoid the lesser incidents which could result in nuclear size explosions and considerable damage to life and property. This is something that we can definitely take action on, and not for a great deal of money either. As I mentioned, for about $30,000 to $35,000, the Spaceguard Centre can get into the business of detection as well as tracking. And given that about 10,000 people usually watch these videos, we're talking maybe £3 per viewer. Not very much, actually, so please check out the link in the description if you would like to support this incredibly important mission. Also, please like, please subscribe, and as always, stay angry about space!